All right, let's pull back the curtain on something truly fundamental, something that really touches every corner of our lives every single day. I mean, countless crucial decisions hinge on our ability to look into the future, right? Think about it. Predicting those subtle shifts in the stock market, or orchestrating the massive logistical dance of a global supply chain, even, humanity's desperate scramble to anticipate and adapt to climate change. Forecasting is just everywhere. It's woven into the very fabric of how we navigate the world, and getting it right, well, it can mean the difference between thriving and, frankly, falling behind. But here's the kicker, and I think we can all relate to this. It's incredibly, notoriously difficult to do well consistently. The data we often rely on is like a constantly shifting river, full of unpredictable currents, sudden eddies, and these underlying trends that are just so hard to decipher. We're talking about time series data, those sequences of information points meticulously indexed over time, like hourly temperature readings, daily sales figures, maybe even the subtle fluctuations in a patient's vital signs. So today we're taking a deep dive into this really fascinating new approach to time series forecasting, something that aims to give these powerful artificial intelligence models, especially those impressive foundation models we hear so much about, well, to give them a truly insightful language to understand this kind of dynamic data.
That's a great way to put it. And what's truly fascinating here, I think, is how this innovation, it's called Wave Token, how it tackles this fundamental, persistent challenge in AI. How do you convert that messy, real-world, continuous information, that constantly flowing stream of numbers, into a precise, discrete vocabulary? A vocabulary that these powerful large language models can actually process and learn from. It's like finding the perfect alphabet, maybe a universal Rosetta Stone, for this constantly flowing river of data. It lets these sophisticated models read, comprehend, and ultimately speak the language of signals in a completely new, much more nuanced way.
Okay, that clarifies it perfectly. So, if that's the core problem Wave Token is tackling, then our real aim today is to break down how it manages this. And maybe more importantly, why it's not just, another model out there, but actually carving out a significant lead, especially when it comes to generalizing to data it's never encountered before. We're talking about unlocking some truly profound insights into how AI can better understand the world around us. This should be interesting. All right, let's unpack this crucial challenge then, time series forecasting. It's far from being just some niche academic pursuit, right? It's absolutely central to high stakes decision making across really vital areas. I mean, in finance, precise predictions can literally mean billions in profit or, devastating losses.
Absolutely.
In healthcare, anticipating disease outbreaks or patient demand, that can save lives. Optimize how we use resources. For supply chain optimization, it's about ensuring products are exactly where they need to be, precisely when they need to be there, preventing costly delays or overstock. And in critical areas like climate science, it's our best tool for accurately modeling environmental changes and preparing for their impact. But,
Ab-
and this is a profound but, doing this well, consistently, reliably, it's always been incredibly hard.
It really has. The complexity, the sheer volume of this dynamic data make it a formidable task. Historically, our primary tools for forecasting have been what we call local statistical models. Think of these as highly specialized, almost handcrafted instruments, meticulously tuned, often painstakingly tailored to fit just one specific data set.
Like a bespoke suit, maybe. Fits one person perfectly, but not anyone else.
Exactly like that. They excel at their particular task, but they aren't easily transferable. You can't just take a model trained on one company's sales data and expect it to accurately predict another's, or adapt a weather model from, say, London to Tokyo without extensive re-engineering. But over the last decade or so, there's been this really significant, almost revolutionary shift in the field. We've moved towards global deep learning models. And the ambition here is much grander. It's about building models that can learn from a vast, diverse array of time series data, and then apply that learned knowledge broadly across many different forecasting tasks without needing to be retrained from scratch every single time.
Right, the whole foundation model idea applied to time series.
Precisely. The immense, undeniable success of large language models, LLMs, in understanding and generating natural language, and even their surprising capabilities in computer vision, that's really accelerated this interest. It spurred a race to build similar foundation models, these generalized AI brains, for other data types. And time series data is undoubtedly one of the prime candidates for this kind of transformative approach.
So, the underlying idea is truly compelling, almost elegant, really. If an LLM is essentially a super-powered pattern recognizer, incredibly adept at spotting subtle relationships and making predictions within complex sequences, Then if we can somehow figure out how to turn any problem into predicting a sequence of discrete tokens, these immensely powerful models could revolutionize forecasting across the board.
Yeah, that's the hope. They've shown this remarkable ability to learn non-trivial relationships through something as fundamental as next token prediction, regardless of whether the inputs represent human language, or pixels in an image, or, as we're discussing today, the ebb and flow of time series data.
But here's the rub, isn't it? Language models thrive on discrete tokens, actual words like cat or dog, distinct symbols, specific numerical values assigned to clear categories. Time series data, by its very nature, is continuous. It's real valued numbers flowing seamlessly, like a temperature reading of 25.3 degrees Celsius. You can't just treat that continuous value the same way you treat a distinct word.
Exactly. The challenge is immense.
How do you convert that infinite spectrum of possibilities into a finite, meaningful vocabulary that an LLM can actually understand?
And this raises a profoundly important question. And it's one that maybe surprisingly has been kind of understudied, often overlooked in this specific context of building foundation models for time series. What is the most appropriate discrete vocabulary or language for a continuous sequential input like a time series? The process of tokenization, that critical conversion of continuous input into a discrete, understandable vocabulary, it's absolutely fundamental. It literally defines the words and grammar that the language model will learn from and then attempt to generate.
So if your vocabulary isn't good enough.
Right. If your chosen vocabulary isn't expressive enough to capture the nuanced patterns, or if it doesn't accurately reflect the inherent dynamics of the data, then even the most powerful, sprawling LLM will inevitably struggle. It'll struggle to make accurate and insightful predictions. It's like trying to describe a symphony using only, say, 10 basic sounds. You're just going to miss most of the richness.
That makes perfect sense. So what are the current ways people try to do this? How have researchers been trying to bridge that tricky gap between continuous time series and the discrete tokens LLMs need?
Well, current approaches tend to fall into a couple of main categories. Each has its own merits and its own limitations. One common method is using temporal patches. This basically means chopping up the time series into small, fixed-length segments, like taking a long sentence and breaking it into short, equal-sized phrases.
Okay.
Each of these segments is then treated as a single token, or maybe converted into a numerical embedding that the LLM can process. Another approach is simply quantizing values into prescribed fixed bins.
Or like rounding things off?
Sort of. For example, if your data ranges from 0 to 100 degrees Celsius, you might create discrete bins for 0, 10, 11, 20, and so on. Each data point then gets assigned to its respective bin, effectively becoming a distinct, discrete token.
And these methods work okay.
They've certainly achieved competitive performance in standard settings. They represent important steps forward in the field, no doubt. However, if we connect this to the bigger picture, these established methods often struggle. They struggle to capture both local and global patterns simultaneously within a single time series.
What do you mean by local and global?
Think about a stock market graph, for instance.
Yeah.
You have the overall long-term trend, right? The broad movement over months or years, that's a global pattern. But then you also have sudden, sharp spikes or dips that are very localized in time. Maybe a reaction to a news event that's local.
Got it. So they're good at one or the other, but not both.
Often, yes. Existing models, by just patching or relying on simple binning, can miss these complex practical patterns. They might capture the broad trend, okay, or maybe the sharp, isolated events, but rarely both with equal fidelity. They tend to smooth over critical details or sometimes fail to recognize the overarching structures. And this limitation is exactly what we see illustrated so vividly in Figure 1 of the research paper we're looking at. Models like Chronos, Times FFM, Moirai, these are big names. They clearly struggle with these real-world challenges. They consistently underestimate subtle exponential trends. They can't accurately isolate and predict those sparse, sudden spikes. And they often fail to capture truly non-stationary signals where frequencies are constantly evolving and changing over time.
Wow.
It exposes a clear, fundamental limitation in their ability to truly understand the nuanced, multifaceted language of real-world time series data.
Okay, so that sets the stage perfectly. The existing methods have limitations, especially with complex, real-world patterns. And this is where things take a truly fascinating turn. You mentioned Wave Token uses something called wavelets. Now, for those of us like me who aren't signal processing experts,
Yeah.
can you give us a quick primer? What are wavelets and why are they such an ingenious fit here? What's the real breakthrough?
Absolutely. And let's stick with that music analogy for a moment because it really helps clarify the elegance of wavelets. The traditional Fourier transform, as you mentioned, is like getting a complete list of all the notes played in an entire song, right?
Hmm.
And how loud each one was. It gives you incredible resolution on what notes or frequencies are present, but crucially, it doesn't tell you when each note happened.
Right, it averages over the whole song.
Exactly.
Yeah.
So for complex, dynamic music like jazz improvisation or a constantly shifting symphony, Fourier struggles because it averages everything across the entire duration. You completely lose that vital temporal context.
Okay.
Now, the short-time Fourier transform was an attempt to improve this. It tries to fix the problem by chopping the music into small, fixed-size windows and then analyzing each window separately.
That sounds better.
It's an improvement
Yeah.
because it tells you when a note occurred, at least within that specific window. But then you run smack into a fundamental trade-off. It's famously known as the uncertainty principle.
Ah, I've heard of that.
Right. If you use a very small window, you get high time resolution, precisely when a note occurred,
Hmm.
but you lose precision on what frequency it was. It's like blurring the notes together within that tiny window. Conversely, if you use a large window, you get excellent frequency resolution. You know exactly what notes are present,
Yeah.
but you lose the precise timing. You don't know when within that large window a specific note actually happened.
So it's always a compromise. You can know when precisely or what precisely, but not both.
That's the classic dilemma. It's a constant, frustrating compromise. Wavelets, on the other hand, are ingeniously designed to overcome this very limitation. They're not like fixed window tools. Instead, they operate like flexible microscopes for signals. They use a mother wavelet. It's a special, quickly decaying, oscillatory mathematical function that inherently adapts its focus.
Def-
It means it can literally zoom in very tightly to give you incredibly high time resolution for quick, high-frequency changes, like a sudden, sharp drum beat in music or a rapid volatile fluctuation in a stock price.
Yeah.
And simultaneously, it can zoom out to give you high-frequency resolution for slow, low-frequency trends, like a sustained bass note in a song or the gradual long-term pattern of global temperatures.
Whoa. Okay, so it adjusts its zoom based on the signal itself.
Exactly. This incredible dual localization in both time and frequency is what makes wavelets so profoundly powerful, and it makes them perfectly suited for analyzing non-stationary signals. And those are the signals that define our real-world signals, whose statistical properties are constantly changing over time, unlike a perfectly predictable repeating sine wave.
That makes so much more sense. So if I'm getting this right, the real breakthrough is that wavelets let you understand both the broad, slow trends and the sudden, sharp changes in your data all at once. Without that frustrating trade-off, it's about breaking down a complex, messy signal into its core components, but respecting both its timing and its frequency simultaneously.
You've hit the nail on the head. Precisely. Wavelets give us what we call a father wavelet for low frequencies. This captures the overall approximation, the coarse, smooth structure, the broad brushstrokes, and then we have the mother wavelet for high frequencies, capturing the detail, the fine, rapid, often sharp changes, the intricate lines, the sudden splashes of color.
Approximation and detail, okay.
We use a process called the discrete wavelet transform, or DWT,
Okay.
to achieve this decomposition. And what's truly remarkable here is that the DWT decomposes the signal, and crucially, it preserves its original length. If your input has n data points, you get n coefficients out. It's perfectly sized.
No data loss or padding needed.
Right. And it's incredibly efficient. It performs this transformation in what we call linear time, ON time.
You mentioned that's faster than the fast Fourier transform, the FFT.
Yes, even faster than the FFT, which runs in ON log n time. This kind of efficiency is absolutely critical for handling the often incredibly long sequences of data found in real-world time series. It makes it computationally feasible to process vast amounts of information quickly.
And this decomposition into coarse and fine components, you also mentioned sparse representations. Does that help the language model learn, make the data easier to digest?
Yes, absolutely. This is one of the most powerful properties of wavelets. They inherently provide sparse representations. It means they concentrate most of the signal's energy onto just a relatively few significant coefficients, while many, many others are very close to zero, effectively negligible.
So it highlights what's important.
Exactly. Think of it like a highly efficient compression scheme for information. Instead of the LLM trying to find patterns in a dense sea of continuous values, It's looking for patterns in a far more condensed, more meaningful set of wavelet words. This sparsity is incredibly beneficial for both data compression and denoising, and it makes the language of time series much more efficient for the model to learn. It focuses the AI's attention on what truly matters, the most informative parts of the signal.
That makes a lot of sense. Okay, so we understand wavelets now, this flexible microscope giving us time and frequency, sparsity. Brilliant. How does WaveToken actually build its discrete, efficient vocabulary using these tools? Can you take us through the exact pipeline they designed, step by step?
Sure, the wave token pipeline is a meticulously designed sequence of steps. Each one is critical for transforming that raw, continuous time series data into the discrete tokens that a large language model can effectively speak and learn from. First up, scaling. The initial input time series gets rescaled using z-score scaling. You subtract the mean of the entire series and then divide by its standard deviation. This step is crucial because the DWT, especially the version they use, isn't translation invariant.
So if the whole signal shifts up or down, the wavelets might look different even if the pattern's the same.
Exactly. Imagine tuning a musical instrument before you play your work. You want all your notes relative to a consistent 0 point. Scaling ensures consistency across all inputs, brings every time series to a common scale. It prevents numerical issues, which is vital for deep learning models learning globally from diverse data. It lets the model focus purely on patterns and shapes, not arbitrary magnitudes.
Okay, step one, scale it. What's next?
Second, decomposition. The scaled time series is then fed into the maximally decimated discrete wavelet transform. This is where the wavelet magic really happens. It systematically breaks down the signal, yielding two main sets of coefficients. The approximation coefficients capturing the low frequency, coarse structure, the smooth trends, and the detail coefficients capturing the high frequency, fine, rapid changes, those spikes, dips, and quick fluctuations.
Got it. Approximation for the trend, detail for the changes.
Right. And this transform is fast, compact, preserves the input size, and concentrates the energy onto fewer coefficients. Super useful for real-world data with sharp spikes. Importantly, the autoregressive structure, the dependency on past values, is preserved within each group of these new wavelet coefficients.
Okay, scaled, then decomposed. What's step three?
Third, thresholding. Now, since wavelets naturally give us these sparse representations, lots of coefficients near zero, the researchers explored several thresholding techniques. The idea is to selectively discard these less significant coefficients without losing vital info. It acts like denoising and compression.
So cleaning up the signal a bit.
Kind of. They tested various methods like Visa-Shrink, CDF thresholding. And here's something fascinating. While some methods like Visa-Shrink worked well for smaller training setups, the optimal choice for WaveToken, especially when trained on larger setups like 8 GPUs, was surprisingly no thresholding for the detail coefficients.
No thresholding. Why not? Wouldn't that keep noisy coefficients?
It seems counterintuitive, right? But with more data and compute power, the model actually benefits from learning from the richer, fuller set of frequencies. Aggressively cutting coefficients early on can sometimes inadvertently harm its ability to generalize to new data.
Interesting. So more data means the model can handle more complexity.
It seems so. But it's worth noting that an implicit kind of thresholding still happens in the next step, quantization. Very small coefficients might naturally just collapse into a zero bin anyway. Crucially, though, the approximation coefficients, the ones modeling the main trend, are always kept unaltered. You don't want to mess with the core structure.
Okay, so scaling, decomposition, and potentially no explicit thresholding for details if you have enough data. What's the final step?
Finally, quantization. This is the pivotal step. This is where we convert those real-valued wavelet coefficients numbers with potentially infinite precision into discrete tokens. The actual words the LLM understands. The coefficients are binned according to their empirical distribution. They use a sophisticated rule designed to minimize reconstruction error, making sure the bins are optimally sized and placed.
So it's not just arbitrary bins, it's data-driven binning.
Exactly. And they also add special tokens, standard practice and language modeling, PA tokens for handling missing values, and EOS tokens to signal the end of a sequence. This entire meticulous process creates a single, shared, compact, yet incredibly expressive vocabulary. a language that elegantly captures both the slow trends and the rapid details. It provides a concise and eloquent representation for the AI.
Wow, okay. That pipeline makes a lot of sense. Scale, decompose with wavelets, maybe threshold, then quantize into smart bins. You end up with this stream of wavelet-based tokens. So how do you actually train an LLM to forecast using them? How does it speak and predict with this new language?
Right, so you have these quantized wavelet coefficients, representing everything from the coarse structure to the fine details. They get carefully concatenated into a single unified vector. This concatenation is key. It allows the model to learn and forecast in a truly multi-scale fashion, considering all these different levels of detail simultaneously within one input sequence.
So it sees the trend tokens and the detail tokens all together.
Exactly. And the researchers thoughtfully paired this innovative wavelet tokenizer with the popular T5 encoder-decoder architecture. T5 is renowned in the AI world for its excellent zero-shot performance, its robust ability to handle complex text-to-text tasks. It's a powerful choice for this new time series to time series translation job.
And you said something interesting before, that concatenating these different coefficient types might seem counterintuitive, like it breaks the time flow, but it actually helps.
Yes, it's fascinating. While concatenating approximation and detail coefficients might seem to break the natural linear temporal structure of the original series, in practice, it turns out to be surprisingly, remarkably helpful.
Yeah.
It provides the model with an inherent natural way to break down complex substructures within the time series. It effectively divides them into a hierarchy of distinct, time-localized frequency bands.
Ah, so the model learns this set of tokens represents the trend here, this other set represents the spike there.
Precisely. The model learns to exploit this hierarchical decomposition, identifying exactly which frequency components are most relevant at different points in time for accurate prediction. This internal organization is a profound advantage for complex, real-world data.
Okay. And the training objective for the LLM itself, is it fundamentally similar to regular language models predicting the next token? Just predicting the next wavelet token instead of the next word.
That's precisely right. The core training objective is next token prediction. The model is trained to minimize cross-entropy loss between its predicted distribution of future tokens and the true categorical distribution of the actual tokens from the future time horizon.
Cross entropy. Why that specifically? Not something like mean squared error.
That's a great question. While cross-entropy loss doesn't directly impose a strict metric onto the vocabulary itself, its flexibility is a monumental advantage in forecasting. Think about forecasting the weather. It's rarely just one precise temperature, right? You might predict a range of possibilities, some more likely than others. Cross-entropy helps the model learn not just the single most likely outcome, but the entire spread of possibilities. It can capture output distributions of arbitrary complex shapes.
Which is much more realistic for real-world stuff.
Exactly. Real-world outcomes are often non-Gaussian. They don't fit neat, rigid statistical assumptions. Traditional loss functions like mean squared error, MSE, or mean absolute error, MAE, often try to make the forecast hit a single bullseye, forcing those rigid assumptions. Cross-entropy lets the model capture the complex shapes and patterns inherent in real-world time series. It means the model understands the nuances and uncertainties, not just a single prediction.
Okay, so it learns the probability distribution of the next token. How does it generate the final forecast then?
For generating actual forecasts, the model samples future tokens autoregressively. It predicts one token, then uses that prediction to help predict the next, and so on, sampling from the learned distribution. These sampled tokens are then dequantized, mapped back from their discrete bin numbers to their corresponding real-valued bin centers. Finally, they're passed through an inverse wavelet transform to reconstruct the time series in its original real-valued form, and then unscaled to return it to its original magnitude.
So it reverses the whole process.
Exactly. This entire loop, from continuous time series through discrete wavelet tokens, processed by the LLM, and back to a continuous understandable forecast, it's truly elegant and remarkably effective. Figure 2 in the paper really paints a clear picture of this whole process.
This really sounds incredibly clever in theory, taking this complex continuous data and giving it this structured, elegant language for the AI. So that's the theory. What happens when you put it to the test? How did Wave Token actually perform against other models on real-world data?
Right. The proof is in the pudding, as they say. And the results are not just compelling, they are, quite frankly, transformative. WaveToken underwent an incredibly rigorous and comprehensive evaluation. It was tested on 42 diverse, real-world datasets. spanning energy consumption, transportation flows, volatile financial markets, intricate weather data, a really wide range.
42 data sets, okay.
And these were strategically divided into three critical groups. Some were just for pre-training, building its foundation. Others were in-domain, used for both training and evaluation, so data the model had seen examples of. And crucially, a significant portion were zero-shot datasets.
Meaning the model had never seen them during training at all.
Exactly. The ultimate, unbiased test of its generalization capabilities, its ability to perform well on completely new, unfamiliar data.
And what kind of competition did it face? Just other foundation models?
No, it was compared against an exceptionally wide and robust range. It included traditional, task-specific deep learning models like DBER, PatchTST, and TFT. Remember, these models are trained separately for each dataset, so they have that advantage of being highly optimized for that specific data.
Right, the specialists.
And it also went up against other recently proposed foundation models for time series, times FM, Chronos, Moirai, Laglama. Models designed, like Wavetoken, to be trained once and applied broadly. So a really comprehensive comparison across the whole spectrum of modern forecasting paradigms.
Okay, and you mentioned three key metrics earlier. Can you quickly remind us? WQL, MASE, and that interesting one, VRSE.
Yes, absolutely. These were chosen to give a holistic view, moving beyond just simple error numbers. First, weighted quantile loss, WQL. This evaluates probabilistic forecasts, how well the model predicts a range of possible future values and their probabilities. Crucial for understanding uncertainty, like in risk management.
Okay, the uncertainty measure.
Second, mean absolute scaled error, MASE. This assesses the accuracy of point forecast, the single best guess. It scales the error by comparing it to a simple seasonal naive model, basically asking, how much better are you than just guessing tomorrow is like today or last year? Provides context and standardization.
The basic accuracy check scaled.
And third, visual relative squared error, VRSE. This is where it gets really insightful for complex patterns. Unlike MAIS or RMSE, which can be fooled by a forecast that's just shifted in time but has the right shape, VRSE measures the difference in the frequency content between the forecast and the actual data. It asks, does the forecast have the correct overall shape? It compares Fourier coefficients at all frequencies.
So it sees the underlying rhythm and form, not just point-to-point matching.
Exactly. Remember that sine wave example? If your prediction is perfect but slightly shifted, RMSE penalizes it heavily. VRSE would recognize the fundamental shape and frequency are correct. Figure 9 in the paper shows this clearly standard metrics fail, where VRSE succeeds in distinguishing visually good but shifted forecasts from bad ones. It captures a deeper understanding.
That's a huge aha moment. The right metric reveals so much more. So how did Wavetoken stack up on these? Let's start with the in-domain datasets, the ones that had seen before.
Okay, on the in-domain datasets, benchmark 1, shown really well in Figure 3, Wavetoken-based and Wavetoken-large, consistently delivered excellent performance. What's particularly remarkable is Wavetoken either performed on par with or often better than all other baselines. It only slightly trailed Chronos Large on WQL and mayonnaise in some cases, but crucially, it was consistently superior on VRSE.
Meaning it captured the shape better, even if the point forecast was slightly off in comparison sometimes?
Precisely. While other models might get the numbers close, Wavetoken demonstrably captured the true underlying shape, rhythm, and frequency content better, a deeper level of understanding. And remember, it achieves all this using a vocabulary of just 124 tokens. Chronos uses 4096.
4 times smaller.
Yes. It empirically confirms that wavelets provide incredibly compact, yet highly expressive representations. More information, fewer words. Wavetoken also got the best average rank across all metrics for these datasets, a very strong indicator of consistent top-tier performance in familiar territory.
That's genuinely impressive, especially with that smaller vocabulary. But the real test, as you said, is generalization. How did it do on the zero-shot datasets, benchmark 2, figure 4, the stuff it had never seen?
This is unequivocally Wavetoken's standout feature. This is where its power for general-purpose forecasting truly shines. It demonstrated superior generalization capabilities. On these completely unseen datasets, Wavetoken didn't just perform well. It outperformed all other foundation models for time series across all metrics.
All of them, wow.
Yes, it achieved an exceptional 83% success rate against Chronos models of the same size, meaning in 83% of comparisons, Wavetoken won. And maybe more astonishingly, it proved highly competitive and often demonstrably superior, especially on VRSE. even relative to those task-specific models that were explicitly trained on those zero-shot datasets.
Wait, so it performed as well or better than models specifically trained on that data, even though Wave Token had never seen it before?
Often, yes. Think about the implications. A single, robust wave token model can be deployed across multitude of new scenarios without costly, time-consuming retraining and still potentially beat the specialists. Again, it secured the best average rank across all metrics on these crucial unseen datasets. Unparalleled ability to generalize broadly and effectively.
That's a huge achievement. A truly general foundation model for time series seems possible. What about long-range forecasting? That's often the Achilles heel, right? Errors compounding.
Indeed, long range is notoriously difficult. But here again, wave tokens showed remarkable resilience. On long horizon benchmarks detailed in Appendix E, Figure 12, where forecast lengths were doubled, even tripled, pushing the models hard. Wave token largely maintained its commanding lead. It continued to outperform other foundation models across almost all metrics. Times FM was slightly better on WQL only in the very longest setting. This shows its robustness for extended predictions. The language it learns isn't just for short-term gains. It enables stable, accurate forecasts far into the future.
For things like climate modeling or long-term finance, that's huge.
Absolutely revolutionary, providing clarity where previously there was mostly uncertainty.
The numbers are incredibly compelling. Wave tokens seem superior across the board, but, sometimes seeing is believing, especially with AI. What does its performance actually look like qualitatively? Can we get a sense of its intuition on complex data?
Figure 1 in the research is absolutely key here. It provides this powerful visual testament to wave token's capabilities. It vividly shows wave token effortlessly capturing complex temporal patterns that other prominent foundation models, Chronos, Times FM, Moirai, really struggle with.
Like what kind of patterns?
For instance, with exponential trends, the others consistently underestimate the growth, smoothing out that crucial acceleration. Wave token nails it. When faced with sparse, sudden spikes, the others often fail to isolate them accurately, missing them or diluting their impact. Wave token captures them precisely. And for non-stationary signals with varying frequencies where the patterns themselves are shifting, the others just can't capture that dynamic behavior. Wave token tracks it accurately.
So it provides accurate forecasts with low uncertainty, even in these really tricky cases.
Exactly. It's a direct observable benefit of leveraging those time-localized frequency bands from the wavelets. It means that the model isn't just guessing well, it's genuinely seeing, understanding, and reproducing the different nuanced components of the signal with remarkable fidelity.
So it's not just getting the numbers right, but truly understanding and reproducing the underlying dynamics. That sounds like a much deeper comprehension. Can we actually peek inside, see how it's doing this?
Precisely. It's comprehension, not just calculation. And what's truly fascinating is we can get a peek into its thinking. The cross-attention layers within the transformer model give us this incredible insight. If we look at Figure 5, comparing the attention maps of Chronospace and Wave Token Base, remember, same TFI architecture on spiky data, Wave Token's attention map is clearly, strikingly structured.
Structured how?
You see a clear division into 4 distinct quadrants. The model learned to attend to approximation coefficients in the input context to forecast future approximation coefficients. And similarly, it attends to detail coefficients in the context to forecast future detail coefficients.
Wow, that's incredibly insightful. It's like it knows precisely which frequency components to look at for different parts of the forecast. It's not just a black box, it has this logical, segmented approach, almost like it's intuitively categorizing the information layers.
That's the perfect way to describe it, and it gets even more striking. For forecasting those crucial detail coefficients, the ones capturing the spikes, Wave Token shows clear vertical columns of much higher attention. These columns correspond directly and precisely to the positions of the spikes in the input context. It even learns to ignore those spike positions when attending to flat regions. It knows when to focus and when to disregard specific details based on what it's trying to predict.
And Chronos doesn't do that.
Chronos, in contrast, shows a much more diffuse, almost repeating, unfocused pattern across its attention map. This lack of focused attention clearly explains its failure to capture the spikes correctly in the time domain. This structured, intuitive, interpretable attention is a direct, powerful result of the wavelet-based tokenization. It gives the model a more effective way to process complex multi-frequency time series.
That's a powerful validation. You can literally see the wavelet approach reflected in how the model intelligently pays attention. Okay, let's talk about fine-tuning this language. I heard the ablation studies had some interesting, maybe surprising discoveries where they tweaked different parts.
Yes, the ablation studies detailed in Figure 6 and 8 are really revealing. They show the careful, iterative design choices that led to Wave Token's superior performance. They show how the language was refined for maximum clarity and efficiency.
What did they find?
First, vocabulary size. They found the optimal size was 124 tokens. And this is significant because increasing it beyond that didn't improve accuracy and sometimes even worsen it.
Really? Bigger isn't always better.
Not here. It's a profound testament to the compression properties of wavelets. They're inherently efficient, condensing complex structures into a compact codebook. A larger vocabulary would just waste tokens on less significant stuff, adding noise. And remember, this contrasts sharply with Chronos using 4096 tokens, 4 times as many often for inferior performance. Big implications for memory and compute.
Efficiency built in. What else?
Second, the wavelet family. Out of many options, the bi-orthogonal 2.2 bases performed optimally. This family has a special dual structure with separate filters for analysis, breaking down, and synthesis, rebuilding. This allows for symmetric wavelet functions, crucial for preventing distortions, especially near signal edges. It's a property known to be good in things like JPEG 2000 image compression. Shows how deep math insights pay off in AI.
So the specific type of wavelet matters.
Very much so. Third, they looked at the decomposition level. Surprisingly, just the first level wavelet decomposition was sufficient for excellent accuracy.
Not breaking it down into finer and finer frequencies.
Right. While deeper levels could provide more granular frequencies, they also create many more coefficient groups. And counterintuitively, this can make it harder for the attention mechanism to identify the most relevant coefficients during prediction.
Like too many ingredients confusing the chef.
Kind of. Sometimes simplicity and focusing on core components works better, prevents the model getting overwhelmed.
Okay. Vocabulary size, wavelet type, decomposition level. What else? You mentioned thresholding again.
Yes, revisiting thresholding. As we discussed, while they tested various methods, no thresholding of the detail coefficients performed best in the final, large 8-GPU setup. This highlights a critical point. With enough data and compute, the model benefits from learning from the full richness of frequencies rather than having them crudely cut off by aggressive thresholding early on. Other methods that smooth the signal too much actually harmed generalization in this large setup.
So let the model learn from everything if you can afford it.
It seems that way. Though remember, implicit thresholding still happens during quantization, where tiny coefficients might hit the zero bin. These ablation choices really highlight how deeply the researchers understood and expertly leveraged wavelet properties specifically for time series data.
So wrapping this all up, what does this mean for us, the listener, in the grand scheme of things? This deep dive into Wave Token vividly shows that for time series forecasting, the very language you choose for your foundation model truly, profoundly matters. It's not just about having powerful LLMs, but feeding them the right kind of information, structured in a way that aligns with the data's complexities.
That's absolutely right. Connecting this to the bigger picture, Wave Token offers a general-purpose forecasting model that's not only incredibly accurate, but also remarkably information efficient. It shows superior generalization, especially on unseen datasets, all while using a significantly smaller vocabulary. It's a powerful testament to integrating deep mathematical insights, like wavelet theory, with cutting-edge AI architectures. It shows us that sometimes the key isn't just brute force compute, but intelligent, elegant data representation teaching the AI a more profound and concise language.
And the practical implications are massive. The ability to accurately predict complex patterns, trends, spikes, non-stationary signals, things that historically challenged models, that's a monumental step forward across countless industries. Finance, energy, healthcare, climate modeling. It's about getting that aha moment of understanding, quickly, thoroughly, without being overwhelmed by raw data. Smarter decisions, faster adaptations.
A clearer path forward.
This deep dive reveals that the future of forecasting might very well lie in models that speak the most eloquent and compact language for real-world data, transforming how we understand, interact with, and predict the dynamic world around us.
Which leads to a really interesting final thought for you, the listener, to consider. If a specialized language like wavelets can unlock such powerful capabilities for time series, what other types of data are out there? Maybe complex images, nuanced audio, abstract scientific data, just waiting for their perfect linguistic key to be discovered. How might this inspiration lead to entirely new ways of building foundation models, new ways to understand the countless complex systems we encounter and rely on every single day?